All right, so what we're going to try to do, again, is tie together what's going on in the game to this sheet, which gives us an introduction to electron configurations and our three rules. So rule number one, electrons enter orbitals of lowest energy first. The game kind of guides you through which orbital comes next. This diagram shows you that in a slightly different way. We've got, going from top to bottom, the increasing energy levels. So this represents the 1s orbital, the box. This is the 2s orbital. And then we have the three different 2p orbitals that fill. And then we go to 3s, so third principal energy level, S-shaped orbital. And then we fill 3p, third principal energy level, P-shaped orbitals. And then what's a little bit tricky at this point is we do not fill the 3d sublevel next. We actually go to the 4s sublevel. So it's in the fourth principal energy level, but it's slightly lower energy than the 3d sublevels. So once we fill those, then we go to the 3d, and we've got 5 different versions, D-shaped orbitals that fill. Okay, so in showing that in the game, most of you did finish the fourth achievement. But here's what it looks like, just to review, or if you don't have it yet, this might help. So I'm going to try to build an atom with 36 protons, which means I need to click out 36 protons in the nucleus. This circle represents the 1s orbital. It can hold 2 electrons. Next up in the order is the 2s orbital. It can hold 2 electrons. And then the 3 different 2p orbitals are represented here. And the rule is I can't pair them up until I fill them in singly. Now I can go back and add 8, 9, and 10. That second principal energy level is now full, the S sublevel and the P sublevel. I've got to go to the third principal energy level. This is the 3s. These together are the 3p. And then notice the 3d is locked at this point. So I can go ahead and put in my 2 electrons in the 3s sublevel. And then I can go 1, 2, 3, 4, 5, 6. Now my p sublevels are full, and you might think again, I need to go to 3d, but it's locked. The next best thing is to go down to the fourth principal energy level and put in 2 electrons in the 4s. Then the 3d unlocks. So now I can come back. Even though these are kind of mostly 4-lobed shapes, they still are an individual orbital, meaning I can put 1 electron in each, and then I can come back and pair them up for 26, 27, 28, 29, and 30. Now the 3d sublevel is full. In fact, the third principal energy level is completely full. My next available orbitals are the 4p orbitals. I need to add 6 more electrons to get to 36 electrons to balance the 36 protons in the nucleus. So 31, 32, 33, 34, 35, 36, and I'm done. Okay, so the order again was 1s, 2s, 2p, 3s, 3p, and then this is where the trick comes in. After 3p, you fill in 4s, you go back to 3d, and then finally you can come back to the 4p sublevel and finish it off. So if I close out the atom, I've created krypton. Okay, and again, in your handout, that is reflected in these boxes. So we go from lowest principal energy level up. All right. So let's talk about how we represent this in a diagram following our rules. I'm going to make my screen a little bit bigger here. Try that again. 300. So what I want to do on this first example is we are going to do the electron configuration for nitrogen, which is symbol N. We would need to find nitrogen on the periodic table. Nitrogen is number 7. What? Atomic number 7. So 7 protons in the nucleus and 7 electrons in the neutral atom. So I need to fit in just 7 electrons into this diagram in the same way I did in the game. So the way that we represent electrons here is actually with an arrow. And the reason for that is electrons have a quantum characteristic or a quantum property called spin. And we say that they have upspin or downspin. That's just the name that scientists decided to give this. And so electrons with like spin have to fill singly, and then you can place them in as pairs. So remember, this 1s orbital was kind of shown as a circle in the game. The way that we show an upspin electron is with an upward pointing arrow. And once you start writing these and you want to be quicker, instead of doing the full, sometimes we'll draw them like that. It's just kind of like a half arrow pointing up. So that's my first electron. The second electron is going to also go in 1s as a downspin electron. My third electron is going to go into the 2s orbital. It was shown as kind of a circle, a double circle in the game. And we're going to have an upspin, that's my third, and a downspin is my fourth electron. And then the 2p orbitals, again, they're kind of dumbbell shaped. I would probably draw them like this, kind of like figure eights in the game. You don't need to show that in your diagram, but that's how it's represented in the game. And I need to put in 3 more electrons. They need to go in singly first. So I'm going to do an up pointing electron. That's my 5th electron. My 6th electron is also pointing up, and my 7th electron is also pointing up. If I had another electron, it would be a down electron here, and then a down electron, but I've done nitrogen, and so I've got 1, 2, 3, 4, 5, 6, 7 electrons shown. Okay. So in writing the electron configuration, which is kind of the shorthand way of showing this, not pictorially, but using symbols, the way that we show that is we write the principal energy level N, that's the number. We write the sub-level letter, S, P, D, or F, and then the number of electrons in that orbital we show as a superscript, like an exponent. So if I want to represent this in shorthand, this is written 1s, 2. 1s is referring to the orbital, first principal energy level, S-shaped orbital, 2 electrons in it. Next up is 2s. It also has 2 electrons. So I write 2s2. That's showing these 2 electrons. The next sublevel that has electrons is 2p. But it only has 3 electrons total, so the exponent here, the superscript, is a 3. That's what we would call the electron configuration for nitrogen. And we'll work with these quite a bit this week. This is a big skill that we're going to use going forward because the electron configuration ends up dictating how that element bonds, how it joins up with other electrons. Okay, joins up with other atoms. All right, so let me go ahead and stop the recording here.